5 parts to this section. It's a little long, but the volume formulas, there's just so much to them that we have to just break it down into 5 pieces. So I'll go ahead and start part 2. Now, I actually want to start by kind of reminding you a little bit about what we were doing yesterday, because you need to be able to compare the DISC method stuff yesterday to this new method that we're going to learn about today. So I would go ahead and copy this down. This is especially important now that we are learning a new method. But again, this is just what we were dealing with yesterday with the DISC method. I'm going to go back and talk about that rectangle a little bit more because it's going to be even more important today. The representative rectangle is always adjacent and perpendicular to the, now I'm kind of abbreviating over here, axis of revolution, AOR, axis of revolution. The representative rectangle is always adjacent and perpendicular to the axis of revolution. Now, when I say adjacent, it means that it's right up against the axis of revolution. I'm going to put back up here one of our graphs from yesterday, actually a couple graphs from yesterday. You don't have to recopy this necessarily, but I think this was example 1. Here's the axis of revolution, the x-axis. Your representative rectangle is touching that axis. It's adjacent to it and it's perpendicular to it. If you went like this and went like that, that would form a 90-degree angle. Same here. The axis of revolution, this was the last example yesterday, that's the y-axis on this one. But again, the rectangle is adjacent to that axis. It's right up against it. And it would be perpendicular. There and there, that would form a right angle. So that's what we were dealing with the DISC method. Now, the new method that we're dealing with today is called the washer method. And last night while I was laying in bed, I thought to myself I should bring in a washer today, and I forgot. But I've got some pictures up here that'll hopefully make it more clear. It says when the rectangle cannot be drawn adjacent to the axis of revolution, when the rectangle cannot be drawn adjacent to the axis of revolution, use the washer method. Now I'll have like a setup for you according to the washer method here in just a little bit. But first, I want to try and put a picture up here of what this is really talking about. You don't have to try and copy this down again. But the bounded region here was just this purple part. And you can see all these rectangles in here. The one that they're looking at in particular is this one, the one in green. And so I'm guessing, since it's being spun like that, this is my axis of revolution. So look at this rectangle. Because our bounded region is basically up higher than our axis of revolution, there's a gap right there. So our rectangle cannot be drawn adjacent to our axis of revolution. It can't be drawn right up against it because that's not part of your bounded region. Our bounded region is up here. So anytime there's a gap like that, and again, it has to be perpendicular. So this is how I have to draw my rectangle. It has to be going this way if I'm spinning around the x-axis. Anytime there's a gap, that's when we use the washer method. If you imagine, and the whole picture's not up here, but if you imagine the rest of this, if they continued to spin this all the way around, it would form kind of like a donut, or in other words, a washer. You'd have a part on the outside that's circular, and then this open circle in the middle. So that's why we call it the washer method. Okay, now, there they are, my washers that I forgot to bring in. I've got two different things to put up here about the washer method. And one part is if you're revolving around the x-axis. Then on the other side, I'll talk about what happens when you revolve around the y-axis. Okie doke. So, setup is a little different here. It says volume equals pi, you still have pi out front, times the integral from a to b of, this has the entire f of x squared minus the entire g of x squared dx. You are still integrating with respect to x when you revolve around the x-axis. The only difference is it's not just a single function that you're squaring like we did yesterday with the disk method. Now there's two functions up here that are being squared and being subtracted. So kind of like what we had to do with the area problems, they're not always going to tell us which function is the f of x and which one is the g of x. So I want to also kind of explain which function goes where. It's similar to what we had with the last section, but that first function, the f of x, is going to be the function on top of your bounded region. Function on top. Now, I also put in parentheses that the function on top is what forms the outside of the washer. I'm going to go back to that picture for just a second. If you look at this bounded region, this, I don't know what these functions are. Maybe this is part of a parabola. That's just a line. But this is the function on top. This would be our f of x. And notice, when that rectangle is spun around the axis of revolution, that function on top is forming the outside of the washer. The function on bottom here, that part is going to fill in the inside of the washer. So that's the next part that I have here. Function on bottom, the bottom part of your shaded region, that is g of x. And again, it's going to form the inside of the washer. It's important to be able to see all of this instead of just writing it all down. You got to really see what's going on with the graphs. Now, I'm just going to put a line up there, and then on the other side, give you some information about revolving around the y-axis. When revolving around the y-axis, we'll be integrating with respect to y. So similar to what we were doing yesterday, but now there's two functions. It says volume equals pi times the integral from c to d of f of y squared minus g of y squared. All of that gets integrated with respect to y. I don't have a good picture of going around the y-axis, but the first function that you put here is going to be the function on the right side of your bounded region. That ends up being the outside of the washer. And g of y, while we're at it, that is always the function on the left, and it will form the inside of the washer. When we start to do more of these problems, it's not going to tell you use the disc method or use the washer method. That's something that you have to figure out. And again, it all goes back to that rectangle. I know we didn't pay much attention to it yesterday, but if the rectangle cannot be drawn right up against the axis of revolution, if there's a gap, then that means you got to go with the washer method. If it's right against it, then you can do the disc method and you don't have to worry about all of that subtraction. Okie doke. So I'll put the directions up here. It's kind of in a couple parts, so I'll give you a second to write that down. Again, it's not telling you which method to use. We'll have to decide for ourselves what we're going to go with. It says find the volume of the solid generated by, find the volume of the solid generated by revolving the region, bounded by the graphs. I'll leave you here. Bounded by the graphs of the equations about the, and part A, we're going to revolve around the x-axis. Part B, we're going to go around the y-axis. Okie doke. And I'm putting a little reminder up here. You can write this down if you want. I don't know if we wrote it down earlier. We actually might have. So if you don't want to copy it again, you don't have to. But remember, the representative rectangle, wherever it's at, it always needs to be drawn perpendicular to the axis of revolution. You have to do that part because, again, that's how you decide which method you want to use. You might need a disc if it's right against it, or the washer method if there is a gap. Okie doke. So I'll go ahead and put the first one up here. Example 1, and since there's 2 parts, this may be the only one that we get to today. We'll see. Y equals x squared plus 1 when x is greater than or equal to 0. And the second function down there is y equals 5. Okay. Now, first thing we should really do is graph this. I've got like kind of a little part of a coordinate plane up here because I can already kind of see what's happening. This first function is only good when x is greater than or equal to 0. So I didn't leave a lot of room on the left. I'm keeping most of my graph on the right. And y equals 5 is going to be up here somewhere, so I left more room at the top than I did at the bottom. Now, you can use your graphing calculator to help you graph this. You won't really be able to type in this part, I don't think. So let me just kind of explain what's going on with our first function. This is a parabola that's been shifted up 1. So my vertex is right here, and I'm not sure how far out I'll need to go, but my next point over, this would be at 1, 2, and I'm not even going to worry about coming out the other way because, again, this function is only good for x values greater than or equal to 0. It's like you're taking that parabola and you're only keeping the right half. You're not even going to have to draw the left half where x is less than 0. Now, if I go one more time, when x equals 2, y should equal 5. So that's probably good for our half parabola. Again, we don't need the left half because x has to be greater than or equal to 0. Then we've also got y equals 5. Now I should probably add a function to our list up here. Our bounded region needs to be cut off right there too, so why not? Let's just add one to our list. X equals 0. That would just kind of cut it off right there at the y-axis. So you don't have to shade if you don't want to, but I'm going to go ahead and do this so you can see exactly what our area looks like. Now remember, we're going around different axes for each part. So part A, we're supposed to spin around the x-axis. What I'm going to do is I'm going to put part A on this slide. I'll probably switch to another slide to do part B because I'll have to redo my graph a little bit. Not necessarily this part of my graph, but my rectangle is going to change when I switch axes. So again, part A, we're going around the x-axis. You can draw the little arrow down there if you want. Now think about your representative rectangle. It always has to be drawn perpendicular to your axis of revolution. Our axis of revolution is the x-axis. So to be perpendicular to that, my rectangle needs to be vertical. I don't care where you put it inside of your shaded region, but it has to be vertical, up and down, because again, it has to be drawn perpendicular to your axis of revolution. Okay, so anywhere in your shaded region, just put a rectangle going from the top to about the bottom. It's kind of hard to cut it off at the bottom since it's a curve. Now, is our rectangle adjacent to our axis of revolution? No. So that means for part A at least, I need to use the washer method because our rectangle is perpendicular but not adjacent. There's a gap. If you took this and you spun it around your axis of revolution, this is going to form your circle in the middle. So when I do my volume, I'm going to have to be careful about which function I put first. Now, before I even do that, I should probably figure out my bounds. And keep in mind, we're integrating with respect to x because we're spinning around the x-axis. So if I'm integrating with respect to x, my lower bound and my upper bound need to be x values. So it's going to be from 0 to 2. I'll go ahead and tell you on part B, when we go around the y-axis, the upper and lower bounds are going to be right here, 1 to 5, because it's going to be with respect to y instead of x. Okay, now I need to fill in the f of x and the g of x part. And it said, this just goes back to the formulas that you wrote down, the f of x is the function on top. The function on top for us is just that horizontal line, 5. And you do have to square it, so I'm starting out with 5 squared minus the function that forms the bottom part squared. And the function that forms the bottom part here is x squared plus 1 squared. Now, again, we'll have to integrate all of that with respect to x. So I need to simplify a little bit first. I know 5 squared is 25. Now, let me figure out this part real quick down here. I'll have to write that out a couple times and FOIL. So, x to the 4th plus x squared plus another x squared. That would be plus 2x squared plus 1. Now, the tricky part is we have to take 25 minus this entire quantity, x to the 4th plus 2x squared plus 1. So I will have to distribute that minus sign, and maybe I'll have a little bit more simplifying to do before I integrate. Any questions up until this point of just setting it up? Okay, here we go. Distribute the negative, and what do I get? I get pi times the integral from 0 to 2 of, let me go ahead and kind of reorder this. This is going to be negative x to the 4th minus 2x squared. Now, this becomes a minus 1. So 25 minus 1, that would be just the 24. You can go ahead and put that there. And again, all of that gets integrated with respect to x. So here we go. Keeping pi out front, I'm going to add 1 to my power, put my new power on bottom. Same with the next part. You can keep the 2 out front, or you can kind of do what I did and put it up with the x cubed. That works too. And then integrating 24 with respect to x, that would just be 24x. Now, the nice part, go ahead. When we distributed the minus sign, this turned into a minus 1. So I went ahead and took the 25 minus 1 and just made it 24. Yep, that is right. Now I'm going to fill in or plug in my bounds. Hallelujah, the bottom bound is 0, so we won't have to worry about that. I think it's going to make everything 0. So let's see what we get with the 2. Now, I should technically keep that negative in front while I take 2 to the 5th power. So I'll work on that more here in a second. When I plug in the 2 right here, I may go ahead and do a little bit of math. 2 to the 3rd power is 8. 8 times 2 is 16. And plugging in a 2 right there, 24 times 2, that'll just be 48. Now, there you are, calculator. 2 to the 5th power is going to give you a 32, but then you have to make it negative. I may just put one more step up here for fun. I'm taking negative 32 fifths minus 16 thirds plus 48. I'm going to have just enough room, hopefully, to type this in. Negative 32 divided by 5 minus 16 thirds. I'm basically putting those fractions in parentheses when I type them in. You get like 36.26 repeating. So I'm going to just maybe say 36.3. And don't forget pi. The pi just kind of hangs out for a while as you work on everything else. Okie doke. Fraction would give you 544 over 15 pi. Okie doke. Any questions about what we did on part A? there was a gap, so we needed the washer method. Now let's go ahead and do part B. And like I mentioned earlier, I'm going to redo my graph real quick. 1, 2, 3, 4, 5. Just because I'm going to have to turn my rectangle around. So if you don't want to redo the whole graph, you don't have to, but this is just me being kind of weird. So there's my half parabola. There's my horizontal line and my vertical line. So same bounded region, but for part B, we are spinning around a different axis. Now we're going around the Y. All right, good enough. So part B, going around the Y axis. If you want to do your little arrow there to show that, you can. And how do we draw the rectangle? The rectangle is always drawn perpendicular to your axis of revolution. So if this is my axis of revolution, the rectangle needs to be going horizontally. That way it forms a right angle with the y-axis. Doesn't matter exactly where you put it, it just needs to be horizontal. Always perpendicular to the axis of revolution. Okay, now take a look at your rectangle compared to your axis of revolution. Is it adjacent? Yeah, there's no gap this time between your rectangle and your axis of revolution. So we're actually not gonna need the washer method with part B. We're just gonna go back and do the disc method because once again, there is no gap between the rectangle and the axis of revolution. Now, I will say that we're spinning around the y-axis, which means we have to integrate with respect to y. So as I set up my bounds, I'm looking at y values. Lowest y value, highest y value. That's going to be a 1 and a 5. Now, anytime you use the disc method, you're just using that main function. I don't have it up here anymore, but it was y equals x squared plus 1. You don't have to worry about subtracting. You can think about if you did subtract right minus left, the left function is just 0, which means the washer method's not even necessary. But because we are integrating with respect to y, I can't just put x squared plus 1 squared right there. It doesn't make sense to integrate with respect to y when your function has x's. So we need to solve this for x. Let's subtract 1 and square root both sides. My square root got a little crooked there, but don't forget, technically we need plus or minus. We're going to say x equals plus or minus square root of y minus 1. That is the function that's going to be squared. Plus or minus square root of y minus 1. You can't put in something with x's if you're integrating with respect to y. So we don't have a 0 as one of our bounds, which is a bummer, but this part works out nicely. Square a positive, you get a positive. Square a negative, you get a positive. And square a square root, it just cancels. So I haven't integrated yet, but I know it's just going to be y minus 1. Okie doke, and here I go. Keep pi out front. Y squared over 2 minus y. And you really don't have any simplifying to do. You just need to start plugging stuff in. So Plug in the 5 first. This will be 25 halves minus 5 minus, here I go again with parentheses in parentheses, plug in the 1, I'll be subtracting the quantity 1/2 minus 1. So maybe I'll just distribute the minus sign real quick. It'll be 25 halves minus 5 minus 1/2 and then plus 1. That's what I need to evaluate, and then I'll just put pi with it. So 25 halves minus 5 minus 1/2 plus 1. That works out pretty nice. It's just 8. So keep pi with it, and our volume ends up being 8 pi. Okie doke. Sometimes you need the washer method, sometimes you need the disk method. The washer method is just kind of like a branch off of the disk method. They're very similar, but again, it just depends on the placement of the rectangle.